Okay. Do you think we can start, Thomas? All right. Okay, so welcome everyone at this new seminar of the event series. And today we host Hans van Tol, or Johan van Tol is his real name, from the National High Magnetic Field Laboratory in Florida and the Florida State University. And Johan is from the Netherlands, and he studied in Leiden till his PhD, where he studied with Johan van der Waals, who is a relative of the more famous van der Waals. And there Hans started studying photoexcited triplet states. And then in the 90s, he moved to the National High Magnetic Field Laboratory in France, in Grenoble, as a postdoc. And then in the late 90s, he moved to another National High Magnetic Field Laboratory here in Florida. And he joined the EMR division. And he started developing his own instrument, an high-field EPR instrument, a super heterodyne instrument, which works at 3 frequency in CW mode, in pulse mode, and he can do also hyperfine spectroscopy experiment. And Hans is a really well-known name and person in the EMR community for these studies. And he got for his career, he got the silver medal from the EPR Society in 2014, a prize that was shared with Stephen Hill, who is a director now at the EMR here in Tallahassee. So today, Johan was so kind to accept our invitation to talk a bit about his expertise in high field EPR and in instrumentation. So he will guide us through this exciting field, I guess. And yeah, the floor is yours.
Okay, I hope everybody can hear me.
Yes.
I don't know exactly how you want to do this. If people have questions while going through the presentation, then they're very welcome to interrupt. Sure. I guess everybody can unmute themselves if they need to. Or
yeah, maybe they can also type it in the chat, and then we can track them and maybe interrupt. Yeah.
Okay. Can everybody see this?
Yes.
So very good. Okay, so I as Thomas said, I'm currently at the National High Magnetic Field Laboratory in Tallahassee, in Florida, in North Florida, and I've been doing high field and high frequency EPR for a very, very long time, actually. So since my undergrad study, I already started in looking at triplet states. It was not so high field. I think the highest frequency was like 60 gigahertz out there, when at least the ones that I used. But first, before I get started with the EPR, I just want to say something of the High Magnetic Field Lab. So Tallahassee has a couple of user facilities. So there is, of course, the DC field user facility, where you can do experiments in continuous fields up to 45 Tesla. And then there is the EPR of the EMR user facility. So we do continuous and pulsed magnetic resonance. And we have like, I think, five permanent staff. And people this is a user facility, so people can come and do experiments. And I'll give you kind of the link at the end of the talk. You can also do NMR. So we have both NMR and MRI. And MRI, there is a magnet which is a 23 Tesla magnet, I think, or a 21 Tesla magnet, actually. For NMR at 900 megahertz, or actually MRI at 900 megahertz. So you can do MRI on small kind of animals and stuff. And we also have the ion cyclotron resonance user facility here, which is ultra high resolution mass spectrometry. But all these are kind of universality. So the DC field is for sure the largest, and the other ones are somewhat smaller, and we're probably one of the smaller ones of these different groups. So there's also kind of a division that does kind of magnet development and both superconducting and kind of resistive copper magnet. So we get kind of researchers from all over the world. So it's the National High Magnetic Field Lab. It is to some extent also international. So our program and the other programs get users from all over the world. So it's a very interesting place to work because you meet a lot of people. So that's always good. So, and nearly every year there's like 20 to 25% of the experiments are done by PIs that are there for the first time. So, and we'd like to keep that number high to attract new users. So if you want to do something, please contact us. So we have a lot of people coming through. So these are numbers from all the different user groups, but there's a lot of postdocs, a lot of grad students. And in many cases, we'd like people to come here. That is not always possible. So sometimes you can just send a sample as well. But then, so I come kind of to the meat. So Thomas, when he asked me, he said, yeah, can you talk about just high field EPR in general and to kind of a tutorial type talk. So I started on that foot in looking and kind of setting up this talk. So there will be some examples of my instrumentation and some other instrumentation, but a little bit of the history as well. So first, I'd like to say why you want to do high fields and frequencies. Well, if you're working at the High Magnetic Field Lab, you kind of have no choice. You have to work at high magnetic fields, but there is actually a lot of scientific reasons as well. I'll give you a very brief history of when it all started, the high field EPR, and then what kind of instrumentation we have, and a little bit about my instruments, and talk a little bit about relaxation, so how that changes at high magnetic fields. And I'll give you an example of some donor centers in silicon carbides. So why at high frequencies? So one of the reasons is, of course, the G tensor resolution. So if you look at the Hamiltonian, so the field-dependent term is typically your magnetic field, and that's the Zeeman term. And if you go to extremely high field, so this is a recent result at 950 gigahertz in one of our magnets of BDPA, which at typical frequencies up to 200 gigahertz, you get kind of a Gaussian line of 10 Gauss wide. But if you go to these very high frequencies, you can start to see the G anisotropy. And these are actually just not quite calibrated well, so there is kind of a shift, perhaps a correction to be made for the isotropic part of this equation, but you can see kind of the anisotropy pretty well. But kind of the first example is actually an example. I'll have to minimize my Zoom window. So that was published from Lebedev at 140 gigahertz, where you see the X-band spectrum. So at low frequencies, so the hyperfine interaction completely dominates, and you don't see too much of the G anisotropy. But then by going from 10 gigahertz to 140 gigahertz, you can clearly kind of get many more features, and you see clearly the splitting of the G tensor. So another reason is that if you're looking at high spin systems, it means where your spin is larger than just your spin half, and you have large zero field splittings. Then
Hans, can I ask you a question? You said I can just unmute myself, right?
Sure. Yes.
I'm just wondering, when you have a better G resolution, which means you know something more about the system, does that somehow contribute to better DFT calculation, because somehow you can have some validation, or how could one use that information? I'm wondering.
Well, so I guess, so of course the G anisotropy itself comes from the spin-orbit coupling. So if you get some experimental numbers for your G anisotropy, it certainly gives you some information for the DFT as well. So you can kind of, so if I don't have a lot of experience with DFT calculations, but I can imagine if the values that you get from your DFT calculations are quite different than your experimental ones, that you might want to look at what's going on.
I was wondering whether for example, G-tensor are typically or commonly used as tools to either check against, validate, or extract from DFT. But
yeah, so
I don't know that.
Yeah. So of course these are really small splittings, and you can think about. I actually wanted to put in an example that I haven't that I didn't put in, but if you, for example, look at amino acid radicals on, you do mutation of a nearby amino acid near your reaction center or your active site. You can actually see small changes in the G-tensor as a function of your substitutions. So it tells you also a little bit of how the environment changes by doing kind of different substitutions of amino acids in the biological system, for example. So in that sense, it helps to kind of, it depends on geometry then, I guess, and these kind of things, and how much coupling you have with the surroundings. Does that, I hope that answers your question. So another reason is, of course, if you're looking at high spin systems with large zero field splittings, and I just give an example of a molecular magnet system. So this is a large molecule where you have 8 iron atoms that are exchange couples. So the spins couple together, and the total spin can end up to be pretty large. And so this is now, in this case, a spin of 10. And you see that at 240 gigahertz in this case, you can see a lot of transitions, because there are a lot of transitions. But you need to have a relatively large field range and high frequencies to be able to figure it out. So at 10 gigahertz, you wouldn't see too much in this particular system. But there's, of course, a whole range of transition metal ions and lanthanides where these things are important. So, for example, this is an iron 2+ complex. An iron 2+ at X-band frequencies is typically silent, so you don't see anything for the iron 2+. So if you go to very high frequencies, and this is an example where the magnetic field is here on the vertical axis to change things around a little bit, and the frequency or the energy levels are on the horizontal axis. And you'll see that for the allowed transitions, they are really occurring in zero field at around 350, 400 gigahertz. So you really need the high frequencies. So in this case, what you do is you choose a frequency and you just scan the magnetic field and see where the transitions are. And in this case, Andrew and Jurek, they used a lot of different frequencies, so you can really follow the complete energy level diagram of these higher spin systems. So this is the spin of 2 in this case. Another reason that you might want to go to high frequencies is if you want to do end or on low gamma nuclei. And this is an example of just a chromium center in a potassium niobate. It actually is a pretty narrow line and a nice spectrum. So you see the central line so is from the chromium, and there is an isotope of chromium that has a nuclear spin, and you can see that directly in your EPR spectrum. But you don't see all the interactions with the potassiums that are surrounding this center, or the niobiums that are surrounding this center. And potassium you won't find too many examples of potassium Endor. I actually had a very hard time to find any examples. But this has a splitting of a nuclear Zeeman splitting that corresponds to about 2 megahertz per Tesla. So at X-band frequencies, this would be like 0.6 megahertz or so. And these are difficult frequencies to measure. So if you do this at 240 gigahertz, so the nuclear Zeeman frequency then is much higher. So it ends up at around 17.5 megahertz. And then you can really resolve the Endor and you can see the individual lines. And one thing to remark, because this is a MIMS Endor experiment, that is somewhat surprising that you have like positive and negative signals if you're looking at an Endor sequence. So in a MIMS Endor, you make a stimulated echo, and then the RF pulse is kind of destroying the stimulated echo. Let me get some water. But in this case, also because the polarization is so high of the electron spin, you actually start to polarize the nuclear spins to some extent. And then it makes a difference. I'm sorry. If you transition level or in the lower spin level, and they end up having a different sign. So you know which transitions occur in the upper level and which transitions occur in the lower level, just by the different sign that you get of your Endor signals. And this is so just to show how this experimentally was measured. So we have, in this case, a Farabi-Perot type resonator, which is mounted below our corrugated waveguide. You can kind of see the mirror below there. The Endor coil was actually going through a quartz capillary that went through one of the nodes here within the resonator. And the sample was glued to the outside of this quartz capillary. So it was not really an Endor coil in a sense, but because the sample is so close to the RF wire, it works actually pretty well, as you see. And then another reason is, of course, that if you don't look at EPR in principle, but at ferromagnetic resonance or anti-ferromagnetic resonance, you get large local fields in these magnetic materials due to the exchange interaction from the surrounding centers. And you can get also magnetic phase transition. So at different fields, your material might be in a different magnetic phase. So this is just an example, also at 240 gigahertz of ferromagnetic resonance in chromium iodide. In this case, it's plotted at kilo-erstat. It's not my usual thing, but our user decided to do that. So this is 6 Tesla and 10 Tesla. So you see that the local fields at the center are actually pretty large. And so we have like a 2.5 Tesla local fields. It's kind of the exchange field at the sides of the chromium in this material. And these are these are van der Waals materials in the sense that you can exfoliate these, and so they have some interest for kind of spin manipulation and spin Hall effect to get interaction with the external field if you make thin films of these kind of materials. And of course, there is an orientation dependent. Part of it is actually due to the shape of the sample. So if you have a thin film, you expect this. But part of it is also due to the anisotropic exchange, and in this case, the Kitaev interactions as well. And then you also have a high spin polarization, of course, and a high absolute sensitivity. So 240 gigahertz corresponds to about 11.5 Kelvin. And that kind of means that if your spin splitting is 240 gigahertz, and then if you're working at 5 Kelvin, your polarization of your spin system gets really high. And that had some kind of consequences that we see a little bit later. But if everything stays the same, you can also increase your sensitivity quite a bit. And not every person, I don't know why this is not an omega, but that is some translation in PowerPoint. But so this is about the absolute number of detectable spins. If everything stays the same, you just scale things down with your wavelength. That your spin sensitivity goes up quite a bit. So almost to the third power in the frequencies. So if you would have a typical 10 to the 10 spins per Gauss sensitivity X band, a W band at 95 gigahertz, you expect something like 10 to the 7 spins, and these are typical numbers that are reported from the different groups at X band. So you can really, for small volume samples, you can have huge increases. However, if you look at the concentration sensitivity, because your sample scales also with frequency to the -3 power, it stays more or less the same. So for concentration sensitivity, you don't get a huge sensitivity gain. And it also means that in many cases, that if you have samples that are not lossy, that a system without a resonator can be more practical, because typically your sample size will be of the order of 1/10 of your wavelength. So if you're working at a 1 millimeter wavelength, which is around 300 gigahertz, then your sample size is of the order of like 100 micron, 100 micron, 200 micron. And it can be becoming quite impractical to load resonators with these kind of volume samples. So in many cases, we actually use no resonator, and I'll show you kind of an example what this could look like. So you just put a lot more sample, and that gains in time, in a sense. It's much easier to get your measurements done, your sample loaded and everything. So that is something that we quite often do. So there is a lot more different reasons. So I showed a little bit. One of them is, of course, also DNP applications. So if you do DNP at 600 megahertz or 800 megahertz, then you get into the very high frequencies. So if you want to kind of measure your EPR spectrum at the same frequencies, you need the high frequencies of the EPR as well. So 600 megahertz corresponds to 395 gigahertz, and 800 megahertz, well, yeah, 4/3 times that number, somewhere in the 500 gigahertz. And then, of course, also orientational selection for Endor. I'll show you a little example for that. But also a faster snapshot. So if you're looking at systems that rotate or have some motion or hopping, going to faster frequencies, it kind of means that you're looking at a shorter time. So what would be completely averaged at X band might not be completely averaged out at the higher frequencies. So you're getting kind of a faster snapshot. And that really makes a difference if you're looking at dynamics in solutions, for example, or spin-labeled proteins in solution. Now, the orientational selection for Endor is kind of clear. So this is one of the first 95 gigahertz papers that came out of the Berlin group with Klaus Möbius. And they show an example of their Endor in some quinone system. So this is, I think, a tetrametal quinone. And so the G-tensor at X-band is not very well resolved, but if you go to 95 gigahertz, you can see it's much better resolved. And then you can do Endor kind of on this side, or you can do it on this side. And you can see that the splittings are different, so you can resolve that. You can also go, this is done at 230 gigahertz or so. Actually 218, I think, if I remember well. So this is just a tempo radical, which is 280 gigahertz, yes. So this is what it looks like in frozen solution at these frequencies, whereas at X-band, the spectrum is actually dominated by the hyperfine interaction along the G direction. But it's going to be hard to separate out the different directions of the crystal. You can select out the G direction, but you cannot really separate the X and Y direction. But if you go to these high frequencies, you can kind of, even if you don't have a single crystal, you can kind of get single crystal-like results. Of course, you're only at the kind of extreme limits. You're really selecting for a single orientation. In the middle, you always have a range of orientations. But you can see that you can pretty well simulate these different hyperfine couplings to the protons. So that gives you to the higher kind of resolution, gives you a way to do your orientational selection. And that can also be the case for things like Eldor. So if you do DIR measurements where you're looking at distances and distance distributions, so there might be some orientation dependence to that as well. So that is something that you can use as well for DIR type measurements. Now, just to switch gear a little bit, I'm just going to talk a little bit about the history. And it kind of, the high frequency EPR, anything higher than 10 gigahertz, more or less, was really pioneered by the group of Yakov Lebedev in Moscow, where in the 70s, the early 70s, he started, I think he got a grant of like 500,000 rubles at the time to build this first spectrometer. And at the time, that was a lot of money. Right now, I think it's $5,000, so it's not that great, but you can see, so this is Yakov, and you might know this one. So this is Mr. Krimov, which he has built some bridges for some of the different groups that at 95 gigahertz and 140 gigahertz. And so this is the example that I showed earlier, actually, but this is one of the first spectra at a 140 gigahertz spectrometer. But from there, and actually, this is Yakov Lebedev, and this is Klaus Möbius. In Berlin, they started to really build a very capable high field, high frequency spectrometer at 3 millimeters, so that is W band, where they employed both the Fabry-Perot type resonator, but also a TE01 resonator, and started doing pulsed quite quickly as well. So, and you see some of the earlier results. This is actually a manganese line that they used as a reference. Also over quinone, I think, in this case. So that was really the start of quite an instrument development. And at the same time, in Leiden, the group of Jan Schmidt was developing also a 95 gigahertz spectrometer. This actually got some early results in 1989 that were published already. And both these groups at the time, of course, got interest by the manufacturer of EPR equipment. So I think Dieter Smolbein and Peter Hoefer came by every now and then to see how things were going and how they could build their own. So that, of course, then resulted in the 95 gigahertz spectrometer from Brugger. So these instruments, though, were really still waveguide instruments. So you use single mode waveguide to go to the resonator. What they did do in many cases, if you have a straight line of waveguide, you might want to taper it up to a larger size just to limit your losses. So the waveguide losses go up with frequency. So even at 95 gigahertz, you have considerably losses. So if you have 1 meter of stainless steel waveguide, which you might want to have in your probe to go to cryogenic temperatures, that gives you like a 10 dB attenuation if you use W-band waveguide. So it makes sense to kind of taper it to a K-band waveguide, go overmode it for a while, and then taper back. But it's still all waveguide. And that kind of changed with the group of Jack Fried, and that was also already in the 80s, where he built a really interesting design where he started to use quasi-optics. So in this case, there was a source and there was a detector. It was a transmission type system in the beginning. And then the waveguide actually was an optical arrangement. So these are all lenses that focus from the initial kind of horn, couple into a Farabi-Perot type resonator, and then go back to the same type of system back to your detector. So this is a very interesting arrangement. And you can see that, yeah, one of the results in the original paper, you can see DPPH at 250 gigahertz, which was really a high frequency at the time. So from X-band to 250 gigahertz, it makes kind of a difference. So if you have single crystals of DPPH, and they're oriented slightly different, so these are all exchange narrowed lines, but still, because of the G anisotropy, you do get some distribution of these G values which you didn't see. So the structure doesn't mean much. It's just kind of the sizes of the individual crystals in the powder. But it shows you kind of the G tensor resolution. And then another group started to come with a kind of a very surprising design at the time, and that was Graham Smith from St. Andrews in Scotland, who really came to the field from an engineering point of view, not so much from a spectroscopist point of view, and he really applied some of the waveguide transportation and kind of manipulation of these high frequency radiation using quasi-optics. So it incorporates wire grids, which are in a sense polarizers. So they reflect one polarization if your electric field is along the wire, and they let they transmit if you're perpendicular to the wires. And then, so you're transporting through free space. You do refocus it every now and then with elliptical mirrors, but it gives you much lower losses in your waveguide transport, or in your wave transport of your microwaves. And then also you have a corrugated waveguide instead of a single mode rectangular waveguide, which is an overmoded corrugated waveguide, which has really low losses. And that was a very unique design. And what is one of the advantages as well is that this, in a sense, is a degenerate waveguide. You have two modes that differ only in their polarization, or actually these waveguides work for linear polarizations in all directions. So you have this cylindrical symmetry. And you can actually use that kind of like a bimodal resonator by coming in to the sample with one polarization. So if your field is along the propagation direction, your absorption, so if you come in with a linear polarization, it's the sum of both left and right circular polarized light. But only one of them will get absorbed. So so one component, the left, depending on what your field direction is, does not get absorbed, but the right circular can get absorbed. So that kind of means that you generate the signal in your cross-polar polarization. And that then has advantages that you're getting much less source noise back to your detector. So you're coming in with a linear polarization and you detect on the cross-polar polarization, which is then called induction mode detection. That is the name that they gave. And of course, you have nice examples of this is a ferromagnetic film, actually, where you see the standing waves, the standing spin wave spectrum. The spectrum will actually depend on the thickness of the film because it's an interference of kind of the spin waves within the sample. So from there, I think things really took off, and a lot of spectrometers are now quasi-optic. And this is kind of a next generation of a quasi-optic instruments that comes also from the Gray and Smith group in St. Andrews. And that is our hyper instrument. So I'll show you some of the instrumentation that we have, but this is the hyper instrumentation. So this is a pulse spectrometer with a 1 kilowatts amplifier. So it's really high power. It is really an interesting quasi-optical setup. You see all these black caps here. So these are all absorbers. And the idea is that if you come in with a kilowatt pulse to your sample, you don't want to have too many reflections, in your spectrometer. So there are isolators in the system that direct the power that is being reflected with the incorrect polarization back to these witches' hats, we call them. But this is, it's using this induction mode that was introduced by Gray and Smith, a very low dead time, and it has a really high power and a high sensitivity at W bands. So there is capabilities also for some DNP at these frequencies. And right now it is coupled as well to an arbitrary waveguide generator. So you can get a lot of interesting pulses into the system. And I think if you're a regular listener to these seminars, you've probably heard about it a couple of months ago. Another spectrometer, which is kind of a really older design, but it's used quite a lot, is a bolometer detected spectrometer. So we have a microwave source here. You go to kind of through gas pipes, go through the sample, and come back through another pipe. That then goes to the bolometer. In this case, we're using this one. So we can use the quasi-optical setup up here as well, but in general, we're using this transmission setup. And the advantage is that you can change frequency by just changing your source. So your detector is a wideband detector. There are no kind of frequency-dependent elements in the system. So you're just looking at your absorption of the microwaves within the sample. And of course, it helps that your absorption probability increases with frequency. So this is very it's very fast to change a sample, and it's very fast to change the frequency. So it's very useful. Although it's kind of a very primitive technique in a sense, it still remains very useful. And the same kind of technique we can also use up to fields at 36 Tesla. So this is a magnet that is what we call the series connected hybrid. It has a superconductor on the outside and a resistive magnet on the inside. And you can ramp it relatively fast. It has a high homogeneity and high stability. Oh, excuse me. And it is kind of a new spectrometer, and currently it's still kind of being upgraded and being optimized. But you can contact Cherry or Urec if you want to do experiments, if you need these very high field experiments. And then something that we also have available at the Mag Lab, so if you want to go to even higher frequencies, is using far infrared spectroscopy. So you do that then as a function of the field, and if you're smart about your background correction, because these infrared spectra have all kind of interferences in your system. But if you treat these well as a function of the magnetic field, you can kind of correct for all these kind of things that are not field dependent. And you can see the field dependent splitting of your energy levels directly in your frequency range. And that is very useful to looking at interactions with phonons and all these kind of things. Now, so, and one spectrometer we also have, and that is a home-built spectrometer that we developed. It's a quasi-optical spectrometer, and this is multi-frequency. So we can change the sources and the detectors to have it operate at each different frequency. So it takes a lot more time than for the other transmission instruments that I showed you. But still, it's about 3/4 of an hour if you want to change the frequency. So it's not too bad. And that has CW and EPR capability, pulsed EPR capability, and transient EPR capability at all these frequencies. So this, what you have on the right is just kind of an MgO substrate, which typically has impurities in it. So there is manganese 2+, there is vanadium, what is it, 3+, and some chromium as well. But you can also see that if you go to these really low temperatures, so we're only looking, if you're looking at this manganese signal here, you're starting to really populate only the -5 to -3 transitions, and the -1/2 to +1/2 transition, which is kind of the sharp line, which is dominating the spectrum at low frequencies. You don't even populate anymore, so you get very high polarization of your signal. So this is also a quasi-optical spectrometer, and one of the and there's kind of a very simple. It's a setup where you measure. There is a local oscillator that just going to the mixers. Your signal goes to the sample. It goes to something somewhat unique, and that is a Martin-Poplet interferometer. So we're actually coming in linearly polarized, but the Martin-Poplet interferometer then allows you to make it circularly polarized, left or right, or the other linear polarization. And then you can measure the different powers that come back in the different polarizations with 2 different detectors. And in many cases for CW measurement, we actually use the power that comes back in the same polarization that you send to the sample to one detector, and the cross polarization to the other detector. And then we mix these 2 signals back together, and this eliminates phase drift because all the path lengths are the same, and it eliminates a lot of phase noise as well. So that helps us in a signal to noise for CW measurements. So the Martin-Poplet said there is one kind of interesting thing that you can do with this polarization. So this is so if you're a manganese 12, I wish I had tested this earlier. So yeah, I can perhaps, So the manganese 12 is a molecule here that kind of behaves like a small ferromagnet at low temperatures. You can kind of get this hysteresis curve in the magnetization. And you have all these different transitions. Now let me actually just, Yeah, move this over a little bit. Okay. So using a right circular polarization or a left circular polarization, you can get different spectra. And the reason is that some of these transitions are left circularly polarized and some of these transitions are right circularly polarized. So if you use just the typical linear polarization induction mode, you get a spectrum like this. But using circular polarization, you can actually select out the different signals with the different polarizations, which is kind of interesting. And one of the things that is kind of useful, has proved to be useful, is that while the radiation always comes down through a horn, so we can change our sample holders and make kind of different sample holders for different purposes. So one is like a Fabry-Perot resonator. You want to use that if you have aqueous solution or very small single crystals. Our most used kind of setup is actually what is referred to as the bucket resonator. And this can be a bigger single crystal, but it can be collections of powders or frozen solutions that we just mount in a non-resonating structure. You can make samples with thin films. So if you have thin films and you can provide some illumination to the thin films, I might give you an example if I have some. Oh, I'm running really late already. And then you also have a bucket resonator where you can excite optically with high power excitation to excite triplet states or transient for transient EPR. And I just wanted to say a little bit about T2. And these are experiments that were done a long time ago, but it kind of started, the story started really a long time ago. This is a PRL from 95. At the time I was working in the high field lab in Grenoble, and that was, we had a graduate student who wanted to do spin echoes at 600 gigahertz. That was 23 Tesla in one of these powered magnets that they had there. So what you kind of had to build your spectrometer in a week, and then you had like a week of doing experiments, and then you had to empty your magnet cell again. And it was this, a quite interesting experiment in the sense that we had two FIR lasers. So these are CO2 laser pulsed molecular gas lasers that provided us with the frequency at 605 gigahertz. And we actually got it to work thanks to the persistence of Christoph Kutter, the grad student. He now is, I think, the director of the Fraunhofer, the Fraunhofer Institute for Microelectronics. But we did find that we could do pulsed EPR. So this is actually BDPA sample. It is quite a concentrated BDPA sample, I must confess, but you can see that the echoes themselves give their own echoes again. So it's we got up to 4 echoes in this particular system. But one of the things that surprised us that if you looked at the T2 in these systems, that it was longer at 600 gigahertz than it was at X-band for these concentrated systems. And then, so we scratched our hands a little bit, but then we kind of hypothesized that the 1 over T2, if you think that the T2 is determined by your fluctuations of your surrounding electron spins, that these fluctuations slow down if your spin system starts to get polarized. So if your spins are all pointing up, there are no pairs of spins that can fluctuate. So, and then, so your 1 over your relaxation rate actually goes down. So so typically, the polarization of your upspin is 1/2, and your polarization of your downspin is 1/2 at high temperatures or low frequencies. But if you now start to, so that comes to about 1/4. So, but if you start to think, if you have 1% polarization, then this number gets much more over kind of a 99% polarization, this number gets really much smaller, and you start to see that. So you just, a simple model, you just kind of, the number of pairs or up and down spins determines your T2 in this concentrated system. So then later on, with Susumu Takahashi, who is now at the University of Southern California, we looked at this a little bit in more detail over a larger temperature range, and we looked at nitrogen centers. So these are either P2 centers, these are just nitrogen substitutions in diamond, and NV centers. So these are the P2 center signal, and then these small signals out here in this that you have to blow up quite a bit to see them are the NV centers. And indeed, so if you go to the low temperature limit, you can see that this is the T2 gets much longer. And this model, the simple model, seems to fit quite well, this model. So for these concentrated systems, the T2 get a little bit longer, and this is kind of the simple model. So if you have a lot of pairs of spins in the neighborhood of the spins that you're looking at, and they can do flip-flops, this will change this spin's environment a bit and just induces a T2 relaxation. But now if all the spins are aligned the same way, there are no pairs that can do these flip-flops, and T2 gets longer. And of course, this is only true if the kind of at high concentration systems where the electron spins themselves are important for the T2 relaxation. So you can then even look at very concentrated systems, which is a single crystal of these iron 8 molecules that I showed you earlier. Of course, you have to be at really low temperatures to be able to even see an echo. So below 2 Kelvin, and you can see it still follows this dependence quite nicely. Now, and I think this is going to be my last slide, actually. So for the T1 relaxation, things are a little bit different. And this is an example in silicon carbide. So these are nitrogen shallow donors. It's somewhat comparable to phosphorus in silicon, except that this is an hexagonal crystal and there is quite a bit of anisotropy. And you have two different sites in this particular polymorph of the silicon carbide. There's a cubic center and a hexagonal center. So the cubic center have much larger hyperfine splitting with the nitrogen. It's also there, of course, in this hexagonal center, but it's less well resolved. But if you're looking at, and this is a very busy graph, I have to move a little bit for the light. So if you're looking just at the T2s in this case, or the T1s, at 120 gigahertz, the T1 is about 2 seconds, actually, at low temperatures. Now, if you go to 240 gigahertz, the T1, let's see, actually, let's go to 316 gigahertz at T1, so that these are these purple ones. So it's about a factor of 30 times faster, so we're less than 100 milliseconds in this case. So that really corresponds to a frequency dependence of the frequency to the power 4. And for the hexagonal centers, the T1 is actually a little faster, it is closer, but you get the same kind of behavior. So your T1 at 120 gigahertz is 10 milliseconds for that center. But then if you go to 240 gigahertz, it is about 0.6 milliseconds. So it's you get this really strong dependence on your T1 relaxation. And this is just because this is kind of the contribution from the direct process. And these are, so your phonon spectrum has a much higher density of states at these high frequencies. So you have more phonons available, more phonon states available to relax to, and that then induces a much faster relaxation. So with that message, I think I'm going to skip this actually. I want to thank you for your attention, and please, if you have any questions, I'm open to it. And also, so if you go to nationalmaglab.org, you can find all kind of information about our lab and also how to apply for time on our instrumentation. Thank you very much.
All right, thanks a lot, Hans, for this extensive talk. It was very nice to hear all these stories and all these experiments. So now I think we open the floor for questions. And Songi, you're very quick in raising the hand, so you go first.
Good that a physical hand worked.
Yeah.
I'm very curious and interested in this T1, T2 at high field, where you talked about highly polarized, and then of course you have the spin burst quenching effect, right?
Mm-hmm.
And then you mentioned something, but I'm getting curious. What happens in a limit of higher and higher and higher concentration and stronger coupling? So for example, let's just take, I don't know, BDPA or something at very high concentration where there is exchange coupling, let's just say, but there are still individual spins. It's weak enough that's a perturbation. Would it be correct to think that if the coupling is stronger and stronger and you are now at very high polarization, your T2 now should become even bigger and bigger, because it's like holding all the spins by a chain together, and they would have a very hard time flipping because of coupling, no?
Well, to some extent that is true, but if you can kind of start seeing this in your spectrum. And so if you're starting to get that much exchange coupling, your line width of your EPR spectrum will get exchange narrowed normally. But once you get to that limit, the line width actually starts to be your homogeneous line width. So your T2 will be still pretty fast in most cases, unless the line gets really, really narrow. And so you have some exchange narrowed systems where you have a really narrow line. And there you can still measure a T2, although...
But I wonder whether that's
mostly hard to measure the T2 because your free induction decay time is actually your T2. And so you cannot really measure an echo anymore because it's just your free induction decay that's limiting it in that case.
But wouldn't it be true that for not in your spectrometer, but typically it's not so easy with a commercial spectrometer to get a 99% polarization? You need something like 7 Tesla and 3 Kelvin, or 3.5 Tesla and 1 point some. So you need a somewhat extreme condition, right? So
right.
In a normal user wouldn't get to the limit, but I'm wondering, when you get to that exchange limit and you get to high polarization, now you have very long T2, and I'm thinking about if people are all dreaming about long decoherence times in the context of quantum information application, right? Is this being used where you just go to this limit of 99% polarization and coupling, and now you have something pretty strongly held and very, very long decoherence time, I think, right?
Well, so normally if you kind of increase your concentration, of course your T2 goes down. So
Usually, yeah.
So your T2 gets shorter. But now you're talking about the limit where everything is exchange coupled. So
exchange coupled and polarized.
Yeah,
100.
so, and I'm not quite sure if you're exchange coupled and polarized, so you kind of get an ordered system in principle. So I don't know exactly how to look at that. But I don't think that there is examples where these exchange actually gets really, really, that the T2 time really gets very long. So in that limit, so your EPR spectrum becomes homogeneously broadened. So you can, like even if you use BDPA as a single crystal, for example, which is exchange coupled, you can get a pretty narrow line, and you can get an FID, but you won't be able to get
An echo.
an echo. Yeah.
Okay.
Okay. Are there other questions from the audience? Anyone can? Yes, we have one in the chat. Can you see this chat, Hans? Or
All right.
what are the possible application of EPR for solid state system coming from solid state physics field? Well,
Yeah, so it depends. It depends a lot. Huh? So at the moment, for example, so our user is looking at battery materials. So this is a solid state material. However, so you're starting to get very broad lines in general because you have such a high concentration of paramagnetic metals in these kind of materials. But in general, so from solid state physics, if you're looking at semiconductors, so EPR is of course very important for defects characterization in semiconductors, and you see that like, well, yeah, or even the NV centers in diamond. That is all. These are all solid state systems, of course. But we look a lot also at kind of magnetic materials. So if you're looking at antiferromagnetic resonance and ferromagnetic resonance in different magnetic materials, where things are starting to get ordered. It's always good to have single crystals, of course, but it's it can give you quite a bit of information. I don't know if that helps.
Yeah, I think this pretty much answered the question. So if there are any other questions, you can write them in the chat or unmute yourself, actually. In the meantime, I have a question, like a brief one. If you, so you showed spectra up to 600 gigahertz or so. And my question is more general. What are the limitations of, in terms of hardware, that prevent the application or the development of higher frequencies in terms of power? Are there limitations in terms of power, or I don't know, pulse generators?
Yeah, so of course, yeah, the microwave technology, if you're looking at kind of solid state devices, so these are typically based on semiconductor materials. So the power goes down quite a bit. So at 950 gigahertz, we have something like 0.5 milliwatt to 1 milliwatt coming out of this source. And then the problem is that you could do this quasi-optically and lose a lot less power, but if you don't do it quasi-optically, you're starting to get significant losses. You're also starting to get in the regime where you have to start working in the vacuum or in some inert gas, because water and CO2 will start to absorb at these very high frequencies. So above 700 gigahertz, you start to have to look at these kind of things as well. But it's there are some kind of ways around. There are like the free of the far infrared lasers, the molecular gas lasers. They're typically not extremely stable at these very high frequencies, but you can get kind of power out of these, which are pretty decent at like 1600 gigahertz or these kind of things. And then we've been looking, for example, at the avalanche kind of, how do you call this? These lasers in the far infrared, the avalanche diodes, but they also don't give that much power in kind of the frequency range that we would be interested in. So at some point, it's kind of the far infrared technology, kind of the Fourier transform kind of spectroscopy, or even terahertz spectroscopy. But typically, your absorption probabilities have to be pretty high. So these are typically used for pretty dense spin systems. Not so much for kind of low impurities or millimolar or micromolar concentrations of spins.
I see. Thanks. Okay. Are there other questions?
Yes, I have a very basic question about high
Yeah.
field and high frequency. So many times we hear about high field and high frequency. So can you tell some limit above which we can consider a field as high and frequency as high frequency?
Yeah, I guess it is whoever you talk to, but I think normally it's a K-band and Q-band is not really considered high frequencies. I think most people put a limit where you need a superconducting magnet or not. So if you can still do things with kind of your 1.5 Tesla sweepable copper magnet, then typically you don't really talk about high frequency. But as soon as you start using or having to use a superconducting magnet, I think then people will talk about high frequency. But it's kind of, high frequency is starting to change to some extent with all the telephone networks, that 5G, 6G, and wherever it's going to go to. But it's approaching kind of the frequency range that we're working at. Yeah.
Thank you.
Hello, I also have a question. Thank you for the talk. Referring to your comment on the increasing concentration sensitivity, could you comment what is the current limit of your EPR spectrometers at continuous wave regime, and what is state-of-the-art concentration sensitivity?
Yeah, so actually, so in principle, you should be able to get some. It depends a lot on what is your spectrum and what is your line. So the problem, if you look, for example, at a thing like a nitroxide radical. So the higher you go in frequency, so typically your line width increases. And your line width typically also increases much more than your CW modulation, or your modulation, field modulation that you can apply in CW. So that doesn't help. You also get some strain in the G values as well. That makes your line a little bit broader. But in general, so if you at 240 gigahertz, the nitroxide will be about 400 Gauss wide, and so it will be much wider than at low frequency. So you have to be a little bit careful how to interpret that. But typically, so the concentration sensitivity, if your line width would all stay the same, it would be pretty close to what you have at X-band, a little bit worse. In the hyper instruments or the pulsed instrument, in principle, you should be able to even do there with the 1 micromolar concentration or something. So there, the excitation bandwidth is pretty wide, so you're exciting a lot of spins, and your overall line is not too broad yet, so it's that helps. I don't know if that helps.
Yes, thank you.
Okay, good. Other questions? Again, you can unmute yourself or write it in the chat. Okay. Doesn't look like we have any more questions, so I think we can close the session here. So thank you, Hans, for your very nice talk.
Well, thank you all for wanting to listen and hanging in there this long.
Yeah,
Thank you.
Yeah, and I remind everybody that the talk will be uploaded on YouTube, so it will be you can re-watch it again. And the next even seminar is in 2 weeks, and we will host Antonin from UCSB, who is working the group of Mark Sherwin and operating the free electron laser. So thank you, Hans, and thank you everybody for listening.
Thank you.
Bye.
Bye-bye.